Hello and welcome to Dr. T Math. In today's episode, we're going to look at functions and piecewise functions and how the algebraic representation is just one side of a coin and tabular representation is another side of a coin and graphical representation is yet another side of a coin because coins have two sides and an edge. They're all just three parts of the same system, and we're going to start off with just kind of a quick discussion of what a function is. We've got an input, and in most cases we're calling that the x, and then we've got an output, and in most cases we're calling that the y. And that's because on our standard Cartesian plane we've got our x and our y, where our x is the independent variable and our y is the dependent variable. And in early algebra, people usually learn about the vertical line test. If we had some sort of function, then we could draw several different vertical lines and make sure that the function does not cross, or that vertical line does not cross the function more than once. And what that means is that we have, for all x's, we only have one y per x. One y per x. We don't have something going like that for two y's. We have one y per x. And we could have two x's for a y, and that would just mean that it doesn't pass the horizontal line test like this function here, but that's fine. That just means it's not a one-to-one function. It can be a many-to-one function. That's still a function. And in real world, I like to give the example of if you put a cucumber seed in the ground, are you going to get a banana one time, and then an eggplant another, and then an onion another, and then radish another? Well, of course not. That's ridiculous. You're going to get a cucumber every time. But if something were not a function, then you could get any output at any time, or you could get multiple outputs, and you wouldn't be able to really predict very well, because you would have at one x value, like for a horizontal parabola, you got one x value and two y values. And so one time you get this output and one time you get that output, and you can maybe develop some sort of scheme where you can predict what the output will be, but then maybe not. So we want one output for every input. If we put a carrot seed in the ground, or if we plant a potato, then we want to get a potato. Just like if we put a dollar in the vending machine, we want to get if we push a button on a computer, if I push the keyboard, if I draw yellow, if I draw blue, I want just that same thing coming out. I don't want to press the black color and get purple one time, and then black another, and then red another. I want the same output for every one input. So that's what a function is. People also exhibit the capacity to be like functions, in that if they are given certain conditions, or if they're given certain inputs, then they might produce some output. And then some people, and sometimes, will give multiple outputs. So these things have application all across the world. And in the most basic sense, a function is just, if you give it this, if you put this in, then you will get that out. And so, like, if you put together two hydrogens and an oxygen, you will get water. If you put together some hydrogen, some carbon, and some oxygen in certain combinations, you're going to get various substances. And it just works that way every time. If you light something on fire, then you're going to get some sort of byproduct, like a chemical reaction. And so, while some people think that chemistry and physics and maths are very complicated, what I like to say is, if you like stuff, then the math might be for you. But also, if you want things to be just what they are, then really math and science are where it's at, because they give you the same output every time. Once you learn how the things work, they just work that way. They don't change it up, except as otherwise influenced, like Newton's laws. they're going to keep doing the same thing unless acted upon by an outside source. So in this case, we got a piecewise function. And let's look at the first part. It says from -3 to 1. So on the domain interval from -3 to 1, 1 or less than -3 to 2 positive 1, we've got the function x squared. So let's figure out what we have there. If we've got x here, then x squared is going to be our output. So let's type in, let's put in a -4. X squared is going to be 16. -3, we're going to get 9. -2, we're going to get 4. -1, we're going to get 1, 0, 0, 1, 1. So we can go and plot that. We're going to have 1, 2, 3, 4. So we got 1, 1, 0, 0, -1, 1, -2, 4, and then it just goes up and up from there. That is a parabola. So it goes something like this. And then we put an arrow there indicating that it continues going. Now this less than or equal to means it's a closed circle there. It's a closed dot, meaning that it's inclusive. We could also write this in a different notation. We could say -3 with round parentheses and then 1 with closed brackets like so, meaning that on the left side it's exclusive. Sorry, it's open-ended, I should say. It's open-ended. Actually, that's not going to be right. Less than -3. My fault. So it doesn't have that. We're going only to -3. We're going to have a closed dot up here at 9. If it had infinity there, then we would have that arrow. But we're somewhere up there with that closed dot. So it doesn't keep going and going and going forever. It only goes to -3. And then let's look at the second part. That's all for the first part. Let's look at the second part. We've got x, and then, well, our output is y on the graph, but really it's just x. So y is equal to x. I'll say y equals x. And over here we've got x squared equals y. When it comes to the equal sign, you can flip stuff around. There's sort of like a commutative property of the equal sign. You can flip it around. It doesn't matter what's on the left and right. Generally speaking, conventional notation means that y is on the left. So we're not going to include 1, but let's just look at if we did include 1, because 1 is just a single point. It's incredibly small on the graph. It's barely even recognizable that we would miss a single point. At 1, we would get 1, and then 2 is 2, and 3 and 3. So for our next part of the graph, we're going to have an open circle. I'm going to draw an open circle around that closed circle to indicate that there is continuity there. And then we're just going to go up in a linear way like so to another closed circle there on the other side, because we do have that less than or equal to. So we've got continuity. We're not missing any points in this area here. We're not overlapping either. We don't have two values because we've got less than here, less than equal to here. So we don't have two outputs at that point, and we don't have any discontinuity. And then let's look at the third part here. We're going to have x, and then y equals -x plus 6. So we'll start again at 3 just to see what would be the y if it were included, even though it's not included. -3 here. So our interval notation for the second part again is open 1, closed 3, and then for the third part it's going to be open 3, and then open for infinity, because infinity and negative infinity can't be reached. You can't get around infinity. It's always open. All right, so -x is -3 plus 6 is going to be 3. So we're going to have an open circle there at 3. So we do have continuity. There's no jump discontinuity. These parts of the function just go directly from one to the other. And then at 4, -4 plus 6 is 2. 5, -5 plus 6 is 1. And it's just going to go down by 1 after that. So we start there, and we're going to go here, and then like so, just going downward. And then I'll put that arrow on this side because it continues going to infinity. So that's a piecewise function. Even though it changes function operations throughout the course of that domain, It is still a function because we don't have any overlap. We don't have two outputs at any one input. And we have continuity. Now, we could have a discontinuous function, but in this case, we have a continuous function. And so we could take the derivative at all points except for where it changes over at 1 and at 3, because we have corners there. So even though we're continuous, we cannot find what the slope is, really, because we've got two different slopes exactly at that point, or we're like in this in-between stage where it's not quite certain. All right, so again, to recap, a function is a set of points which is often expressed in a line or a curve, or parts of a line or a curve, where we have only one output for every one input, because we don't expect to get an oak tree from a maple seed and a piece of corn from a cantaloupe seed and these types of things. If we step on the gas in a car, we don't expect the car to stop. That would be the opposite pedal, the brake. We got only one output for every input. If we type the A key on the computer, we don't expect a space, and so on. Otherwise, there's something wrong. And then, if we have continuity, we don't have any overlap of points on the y-end, but also we don't have any spaces, any gaps, holes, jumps, anything like that. And we can express a function algebraically, graphically, and in a table, because these are just three parts of the same system. All right, this has been Dr. T Math. Thanks for watching.